Hi, this is your first video on rational functions for this quarter or semester, depending on what system we're on when you watch this video. And here is your essential question. So how do I find the important characteristics of rational functions? We are going to be graphing these shortly, and so I just want to get used to the vocabulary and then get used to just finding the components. Remember, when we're looking at rational functions, most of the graphs are going to mimic characteristics of the parent function f of x equals 1 over x. You will see other graphs in this section that you're working on over the days that it does not necessarily look like one of these graphs with asymptotes. So what are we going to find? We're going to be able to algebraically, not just on the graph, but algebraically find the vertical asymptotes, which go up and down. So here's your vertical asymptote here. You like the little ants on the graph? And then the horizontal, which I know you're really good with direction, is right here. And you can see that this horizontal asymptote is not at y equals 0. So you can see that. We're going to learn how to find those. And then just as a reminder for vocabulary purposes, I'm letting you know that, remember, asymptotes, what do? They help us understand the end behavior of the function. So we do not have to keep plugging in values of x to figure out what's happening with the y's. So here's some additional things we're going to look at, which is how to find the x and y intercepts for the rational functions, which we're used to doing. And then this is new. We're going to be able to find holes in the graph. So we've looked at piecewise functions before, or, you know, the functions that have different parts to it. So just as a reminder, you've had some graphs that look like this on that function kind of idea. So there might be a hole here and then a dot up here for your graph. So we're going to learn how to find those holes in this section, and then finally test points to figure out what is actually happening with the graph in a more accurate way. Remember, these are estimations of the graph. These are not exact pictures of the graph. Okay, so we're going to go ahead and get started on vertical asymptotes that you already have a lot of background on. So we have this function, and it is a rational function because there are x's in the bottom. And we're going to first start by finding the vertical asymptotes and the domain. So I'm actually going to start with the domain because that's connected to the asymptotes that we're going to find. So what is the domain? Okay, so if you recall, you don't want the bottom to be 0. And so there are a variety of ways and forms that that bottom can show up. When we were doing this earlier, we factored, and so I'm going to quickly do that. So if we go through and factor this, the GCF's 2, and then I'm going to go straight into the factoring because the point of the problems today are not the computation, but what the computation means. So these are the values, remember, that we cannot equal to 0. That's going to help us find the domain. Okay, so x cannot be 10 and x cannot be -2. So when we find that domain, you don't have to draw this picture out. But I know for some people it's been helping. We have a gap in the graph, and then at -2 we have a gap in the graph. We have a gap, there we go, gap in the graph, and so that gives us 3 distinct areas. So just showing you that, and then you're going to write your answer in interval notation. And I think we're pretty good, but again, if you need help on this, let me know. I will be more than happy to help you. Okay, so that's the domain review concept for us, and then we're going to move into your vertical asymptote. So how's the vertical asymptote connected to the domain? Well, remember, vertical means up and down. I'm just going to shorthand the word asymptote to ASY. And here, when I made the number line for you, I actually put in these gaps in the graph. Now, this isn't going to always happen, so this is just the beginning of the learning process. In this problem, what we have are, in fact, 2 vertical asymptotes. So based on the domain, I'm throwing out x cannot equal -2, and I'm throwing out that x cannot equal 10. That happens to be where our vertical asymptotes are. Okay, so these are exclusions. I know that's where the vertical asymptotes are going to show up. So the way we write that is, remember, we want to know where the vertical asymptote is. So we know that it's x equals -2. That's why it's equal to when it's being asked this problem. And the other one is 10. Okay, so we have our first domain in vertical asymptote. Okay, so the vertical asymptotes were pretty easy to find because you've had a lot of experience with domain. The next section you're really going to have to study. So there are 3 cases for the next asymptote we're going to find. We want to figure out the horizontal asymptote, so the one that goes across. And there are 3 different cases, and this is where we're going to actually learn why our parent function, so I'm just going to go ahead and draw out my parent function here, make a sketch. I'm not going to actually go super accurate because you know your parent functions really well at this point. And I'm going to make my highlight. So here's the vertical asymptote because x cannot equal 0. But we haven't really talked about this horizontal asymptote. You just kind of memorized it because we were learning the parent graphs. So this parent graph has an asymptote at y equals 0 because of the following. And every problem like this that has this property works this way. So if the bottom power, so the bottom, okay, bottom meaning the denominator, right? Degree, so the highest power on the bottom, so if the denominator degree is larger than the top, which is the numerator, it will always be the case that the horizontal asymptote will be found at y equals 0. Always, 100%. So when I go back and look at my parent graph here, it's power 1. And even though it's a constant on the top, what we really have is power 0. That's where the constant comes from. So this is the case. So case 1 is where, here, I should put it in the same color for you so your eyes know what to look at. So case 1 is where I'm just going to call this the bottom here. So the bottom degree is larger than the top degree. Okay, and so what will happen with your case? It will always be horizontal asymptote at y equals 0. I'm still in case 1, and I should write out the horizontal asymptote when it follows this situation is y equals 0. Okay, so I'm going to come over here and look at my exponents. So I have 1 in the top, so 2 is bigger than 1, and remember this is the bottom and this is the top, so y has to be 0. So I'm going to go back and highlight for you what I'm looking at. Okay, so that's the first example. So the next example, again, the bottom is 5 and the top degree, right, the highest power on the numerator or denominator, that's what you're looking at. So we've got 5. The degree 5 is bigger than 2. So then again, y has to be 0. So it's kind of nice that that asymptote ends up being the same each time that you're doing this. And then last but not least, remember if I have a constant on the top, we have an invisible x to the 0 here that exists. Why? Because x to the 0 is 1. So if you're wondering where that's coming from. So what I really have is I have the bottom is 2. The bottom degree is bigger than 0. So again, our horizontal asymptote is at y equals 0. So that is case 1. So I'm still looking for those horizontal asymptotes, and I'm now in case 2. So I have an example for you, and I'm going to compare the degree of the top of this rational function, degree of the bottom. This time what I want you to notice is that the exponents have the same values, so for the degree. So it's 3 and 3. So what you're going to look at when you're finding that horizontal asymptote is if the degree on the top and bottom are the same. So I'm just going to write the term with the degree on it, what happens is we get the horizontal asymptote at 4/3. So what is the case? The case is the powers are the same. So the degree on the so the degree of the top equals the bottom. So y is equal to the coefficients. And I'm going to say coefficients reduced, so you understand that we're talking about the fraction. And we want to try to keep those in fractional form, but in the reduced form, so please don't turn them into decimals. Okay, we're going to do a couple examples. All right, so in my first practice problem that I have for you, there isn't any degree, so I'm going to write the 1 because there is. And I'm going to write the y value here. And then if you notice, I have a negative x here. So when I go to reduce, I actually get a horizontal asymptote at -4. Okay, and that is reduced again, so that's the horizontal asymptote. Okay, the next example, I have power 2. And I'm going to come over here and write my work. What we're really looking at is the ratio of the coefficients. So this is x squared. And if I go ahead and do the cancel again here, or I shouldn't say cancel, but the 1, right? We're simplifying. What you really have is, it'd be real easy to go, oh, I have nothing here, but you really have an invisible 1. So I'm just reminding you, you need to put the 1 and then it's over 11. Okay, so that's case number 2. So if the powers are the same, you're going to take the coefficients in reduced fractional form. All right, we are at our final case now. So our final case, remember, we're looking at degrees of the numerator and denominator. So I'm going to go check out my degrees again. I've got 2 and I have 1. So this time the numerator, or the top degree, has this kind of relationship. So the bottom, or the numerator degree, has this kind of situation. So it's 2 and 1. So what I've now shown is that the top is bigger now than the bottom. So this is switched from case 1. Okay, so that's that top. So this is 2, and then that's greater than 1. Okay, so what is the case going to tell us? It's actually going to tell us we don't have one. We don't have a horizontal asymptote. So no horizontal asymptote exists. Because what you will end up having, okay, remember horizontal goes in this direction. In this particular example, what we're going to have is what we call an oblique asymptote, which is not horizontal. So there is an asymptote, it's just not horizontal. So that is case 3 for horizontal asymptotes. So we're going to write the top degree is greater than the bottom degree. And we know that we have none. All right, and it'd probably be a good idea if you took case 1 through 3 and summed them up in a way that makes sense to you, so you can remember which rule goes with which case. Okay, and we're going to start doing some examples. This is the example that we started with at the beginning when we look for vertical asymptotes. So now we're looking for that horizontal asymptote. I'm reminding you down at the bottom of the 3 cases that we've just looked at. So case 1, 2, and 3. And remember, we are comparing the degrees of the top and bottom. So when we look at this, I have the top is 1, and I have the bottom, the degree power is 2. So I know it's not going to be number 2 because the exponents are not the same. And so the bottom one is bigger down here. And if you go back and look at your notes, if the bottom degree is bigger, then we know by default it's going to be y equals 0. Okay, so I'm going to write that down. So this is y equals 0. And it's that easy if you know the cases. So now if the function is given in factored form, we still have to be able to find the vertical asymptotes and, in this example, the horizontal asymptotes. So what if it's in factored form? So what you want to do is figure out what the degree is going to be. So this is degree 1 and degree 1 because there's nothing there. And so the top has degree 2, so I have an x squared. And remember, I have a coefficient out here that's 3. Okay, and I shouldn't put an arrow, equal sign. I should kind of put an arrow there so you have a better idea of what's going on. And then on the bottom, when you look at it, this is power 1 and this is power 1. So again, we're at power 2 again. And then I'm just going to take the coefficient, which is 2. So as you can see, we're now going to figure out, well, which case do I have? Okay, I do not have the case where the bottom is bigger than the top degree. So I don't have that one. Okay, I do have that the bottom degree is equal to the top degree. So that means I'm going to take the reduced fraction of the coefficients. So that means that y is equal to 1.5, which is 3 over 2. So if you want to change this to 1.5, I mean, I think that that's really, well, it's an exact value, but also, you know, most people know what 1.5 is. The problem is if you're asking me about fractions, is if you get like something like 1/3 and you turn it into a decimal, that's a 0.3 repeating. And so I would prefer you keep it as a fraction. But for terminating decimal, which 1.5 in, that makes sense that you're going to do that. All right, so we've seen one that has standard form polynomials on the top and bottom, and then we saw one that is in factored form. Okay, so I'm going to do the last case. All right, we're comparing on this next example, so it's not in factored form, so I'm just going to go ahead and believe the exponents that are there. So I've got 2 on the top for the degree, and then I have 1 on the bottom. So I have that the bottom is bigger than the top. So which one of these? And I went ahead and erased them, so it kind of forces you again to go back and look. So y equals 0. This is where the bottom is bigger than the top. So by default, it's y equals 0. So now I have to go back and fix this because I just realized that the top is bigger. So if you're like, oh, what's going on? You're right. So the top power is bigger than the bottom. Okay, so it's not going to fit case 1. Okay, case 2, remember we're talking about the bottom is equal to the top degree. We don't have that. And then finally we do have that the top degree is bigger than the bottom. Okay, and again, I mean, I know I even listening to myself, I can tell like when I'm saying it, it sounds confusing because it almost sounds the same, but it's not quite. So go back and look at your notes. Okay, you have to with these cases. So if the top degree is bigger than the bottom degree, then I know I don't have one. Okay, so y equals is none. We don't have a horizontal asymptote. Remember, I let you know that a lot of times you'll have asymptotes that look like this. You'll even sometimes have asymptotes that look up like a parabola. But we're not doing that in this lesson. So the rest of the video may not be synced, and that's because I didn't realize I put myself on mute when I was explaining this part. It's really important. So what is a reduced rational function or reduced function? Okay. It's important because it's going to show us what the graph looks like, and it's denoted by r of x. Remember, it's not the original function, it just kind of looks like the reduced form. So you can see I gave you a function that's already factored, which is great, and then we're looking for factors in the top and the bottom that are exactly the same. Because if the factors are exactly the same, then we can go ahead and calculate that to be 1 or cancel out the parentheses, but remember it's becoming 1. So this is the reduced fraction. And remember what I said at the beginning, which is the graph looks like the reduced function, okay? So now in the purple, what I'm doing is just reviewing with you how to find the vertical asymptote. And remember, it's connected to the domain. And then we're looking for the horizontal asymptote, and we see that the degree on the top and the bottom are exactly the same. So we know that the horizontal asymptote is at 2 over 1, which is 2. All right, so we're doing another example of this, but this example is really special, and you're going to see these in your practice. So what's the reduced form? It's r of x, right? So you're going to take the original function, which is f of x, and you're going to factor it, right? The previous problem was already factored, so that's great, but you're going to factor this. Okay, you find your the same factor on the top and bottom to reduce. And there's something special about this reduced function. So I'm going to rewrite this function in a way that you recognize much easier. Notice there's no x in the bottom. Okay, there's no x in the bottom of this. So the graph looks like this, and maybe some of you can already see it, but if you can't, we're going to keep going. So the 1/3 on the bottom can be rewritten. And then I'm going to distribute out the fraction. And I'm reminding you to put the 1s underneath, because then you just do the distribution straight across. And what you should see now is you have a linear function. So this actually isn't one of those functions that looks like the parent function. It's still a rational function, right? Because we have a fraction. But the actual graph looks like a line. And this is why we need to understand how to do reduce. So it's not f of x is equal to 1 over x. So the reduced form helps us find the holes in the graph, and we've seen some of those in previous exercises you've done. And then we have maybe like a little dot on the outside, but the goal here is to use the reduced form for the hole.